So here I am in my Google Colab. Let us start with importing some of the important libraries. So I'll say import NumPy as NP. I'll import pandas. I'll import matplotlib. I'll import Seaborn as SNS. Before moving on, again in Google Colab, it is highly recommended that you should turn off the AI assistance. That is good for you, especially if you are in your learning phase. So go to tools here. In tools, you should find the settings. In settings, you are looking for AI assistance and just uncheck this one, right? So just uncheck this and you're good to go. All right, it is highly recommended that you do that. Now I'll import from scikit-learn a data set. All right, so I'll say make blobs and I'll say number of samples as, let us say, 300. So it creates a synthetic data set using the Mac blobs function. So it is going to contain 300 sample with two features and is clustered around two centers, and standard deviation of the cluster is, let us say, 1. I'll say some random state as well, 101. Assign this to some variable. I'll call this as maybe I'll call the data, right? And so if you check your data here, is going to be a tuple where first one is the array. You can say it's a tuple. You can check this out if you're not sure. You can say type in data, it's a tuple, right? So inside this tuple, the first thing or the first component is your array, that is your feature. And the next one is y, right? That is the label. So I'm having x for the feature and y for the label. All right. And now you can just check y here again if you want to. You can see there are two cluster here. So centers are 2, thereby I'm having 0 and 1. All right. And x again, you can check this if you want to get the shape. You'll see that it is having a shape of 300, that is the number of samples, and 2 being the feature. So this x1 and x2, and that y was basically the y, right? It was the label. Now, I'm going to generate a 1D array of normal noise from a normal distribution. So I'll say np dot random dot seed and pass in maybe 101. I'll say z noise equal to np dot random dot normal size equal to length x. So here we have created this z noise here, and if you check z noise, you can see it's an array again. Now what I'm going to do is I'm going to pass this as a series, and you'll understand why I've done that. But let me for now, so basically I'm creating the data here, and I'll be using the same data so that we don't have to use an external data, right? So this is my z noise. Right, I've converted the array of noise into a panda series, which is a one-dimensional labeled array capable of holding any data type. Now, I'll do one more thing. I'll say pd dot data frame, pass in x here, and assign this to, let us say, feature. Then I'll say pd dot concat feature noise and x is equal to 1. And if you run that, you have this. Now this is feature as this. I'll do one more thing, that I'll take the, and this I'll say as x1, x2, x3. Right, so I'll say feature dot head as this. Just a second, this has to be equal to. All right, so we have basically created this data frame. Now, what is the point of this? If you just try to plot this out, you will see that plt dot scatter between any two things or any two feature x1, comma x2. All right, and if you just take the coloring, color equal to the y label that you had created. So if you run that, you can see this is the, two x1 and x2 that we had previously. All right, great. Now, I'll also try to show you the 3D plot. Now, 3D plot per se, it is not actually very important for us to, we don't have that much of use case of 3D plot, but you can use this and you'll say MPL toolkits dot mplot 3D import access 3D. I'll say plt.figure as this and figure equal to this. All right. Then I'll say x equal to figure dot add subplot. And I'm just saying that number of rows is 1, 1, 1. All right. And then projection. Okay. Then I'll say x dot scatter, pass in feature x1 and x2 feature. So I'm trying to plot everything here, right? In 3 dimension, and color is equal to y as well. All right. So you can see this is the thing that I'm getting. Okay. Now let us get the next thing up, that is encoder and decoder. Right. First one is import torch torch.nn snn torch.optim optimizer as optim. I'll also import from pre-processing. I have to import min-max scaler as scalon dot pre-processing import min-max scaler. Dot. All right. Again, Torch imports the Torch library, which is built for training. It is used for building and training neural network in Python. And then you have the NN module that provides classes and functions for constructing the neural network. Then we have Optim module, which provides the optimization algorithm for training neural network. Next is we have to define the encoder. So I'll say class encoder is going to inherit everything from the nn.module class, the base class for all the neural network modules in PyTorch. And then inside that, we'll have the constructor method, that is def underscore underscore init underscore underscore self. And then I'll have super encoders. It calls a constructor of the parent class self.encoder layer, that is nn.layer 3 by 2. So I'll say encoder comma self dot underscore underscore init underscore underscore self dot encoder layer equal to and dot linear and 3 by 2. I'll say def forward self comma x and return toss dot relu self dot encoder layer x. All right. Uh, so we have gotten this forward pass here of the encoder. So the input x is passed through the linear layer and a relu activation function is applied to the output. Then we have to define the decoder. Sorry, this is class decoder. Again, it is going to inherit everything from the nn.module. And I'll say def underscore underscore init underscore underscore self. And is going to have super decoder comma self dot underscore underscore init underscore underscore. And then I'll say self dot decoder layer equal to nn dot linear two by three. Then you'll have the forward pass self comma x here, and it's going to return toss dot relu and self dot decoder layer x. Okay, now we have so we have gotten the decoder class here. Just to explain this, it defines a decoder class similar to encoder. Self dot decoder layer. Then you have the nn dot linear 2 by 3 defines a linear layer with a 2 input feature and 3 output feature. Then we have the forward pass of the decoder applying a ReLU function after passing the X through the linear layer. And then we'll have to define once you have the autoencoder, we have the encoder and decoder. Then we'll define autoencoder here. Autoencoder and then dot module. Let's say def underscore underscore init underscore self. Then I'll say super autoencoder comma self dot underscore underscore init underscore underscore. Here is this. Also self dot encoder equal to encoder self dot decoder equal to decoder. Okay. Then lastly, I'll also have the forward pass as the encoded equal to self dot encoder x and decoded equal to self decoder. And we obviously in decoder we have to pass in the encoded part, right? And then I'll return the decoded. All right. So again, what you have done in this autoencoder class is we have combined autoencoder and decoder. encoder, it creates an instance of the encoder class. This creates an instance of the decoder class. Then this defines the forward pass of the autoencoder. The input X is passed through the encoder to get the encoded representation, and then through the decoder to construct, or should I say, to reconstruct the original input. Now what I'm going to do is I'm going to instantiate the model. Hopefully everything is fine that we have done. So I'll say autoencoder, and then we have autoencoder here. There we go. Next is to define the loss function. So I'll say criterion equal to nn.msc loss, and optimizer is equal to optimizer dot stochastic gradient descent. And then I'm taking that instance that is autoencoder, and I'm calling the parameters from this. Learning rate equal to 1.5. All right, so it defines the autoencoder as a stochastic gradient descent that is responsible for updating the model's parameter to minimize the to minimize the loss. And then autoencoders dot parameter, it passes the modus parameter to the optimizer. Learning rate being 1.5 is the controls how much to change the model in response to the estimated error each time the model weights are updated. So this is the optimizer here. All right, then I'll scale the data. So I'll say scalar equal to min max scalar, and then scaled data equal to scalar dot fit underscore transform. Just wait. Right. Then I'll say scaled data tensor equal to tosh.tensor as scaled data, and d type equal to float 32. So I'm mentioning the data type here. Sorry, this tosh.float 32. All right. So again, it converts this one actually tosh.tensor. It converts the scale data into PyTorch tensor with a data type of float 32. Tensors are the core data structure in PyTorch, similar to the arrays in NumPy, but with additional functionality for GPU acceleration. Then I'm going to train the I'll train the autoencoder here. And for that, I'll first have to define the epochs. I'll define that as at least 15. And I'll say for every epoch in range epochs, I'll say optimizer dot zero grad. That clears the gradient of all optimized autoencoder here. And then gradients from previous step are accumulated by default, so they need to be resetted at the start of each training step. Then I'll say outputs equal to autoencoder and pass in the scaled data tensor. So it passes the scale data tensor through the autoencoder to get the reconstructed output. And then we have the losses. So I'll say loss equal to criterion, pass in the outputs, and scale data tensor. Then loss dot backward that computes the gradient of the losses with respect to the model parameter. This step is crucial for the optimizer to know how to adjust the weights. And lastly, you'll say optimizer dot step. So uh, this updates the model parameter based on the computed gradient to minimize the losses. But let us now print this. All right, so I'll print the current epoch number. Okay, then loss dot item. All right, so that extract is the external scalar value from the loss tensor. Then I'll say encoded 2 dimension equal to autoencoder dot encoder here, then say scaled data tensor dot d dash dot numpy here. All right, so it passes the scale data through the encoder part of the autoencoder to obtain the 2D encoded representation. Then dot detach method is used to create a tensor that is no longer connected to the computational graph, meaning it won't track gradients. Then numpy converts the tensor to a numpy array to easy manipulation and visualization. I'll say plt dot scatter. Let's say encoded 2 dimension as 0, then encoded 2 dimension as c equal to y. I'll say plt dot show. Let us run this. Hopefully I'll not get any error. Let us run this. All right, I have gotten the error and that is in here. So yeah, after detach we have to put a a bracket. So let us run this now. Right, so we'll let it run. Okay, it has finished. It is it has already finished, but it has done quite a good job. So you can see here that it has worked perfectly fine in case of damage reduction, right? So after every epoch, we have gotten the losses as well, right? And this is after epoch number 15. So we are not getting, we are not getting any substantial reduction in the losses after a certain point, right? Oh, it's the same thing maybe. Let us see what is going on here. Uh, let me check this out because there has to be some issue here because we are only using the encoder only, right? So that's completely fine. But the problem is this has to be outside of the for loop. And that is why I'm getting this. And if you run that one more time, lastly, there you go. So now we are getting a decrement in losses, or are we? No, we are not. Oh, we are, right? 0.19, then 0.08, and that's it. There's not much of decrease after a certain point. How about this one then? Just a second. Okay, let us do this. Put this in the same cell as this one. I don't think it will matter that much, but let us put that in the same cell here as this. Right. Let us run everything. Yeah. So it's working fine. You can see here that we are able to, reduce the dimension of our data from, 3 to 2. Okay.